Hi everybody, welcome to Environmental Geology and to our first video called Plate Tectonics and the Rock Cycle. In this video, we're going to go through a couple of the most basic concepts of geology that will really provide a framework for some of the geology we'll be learning over the next couple weeks in this class. So specifically, we're going to look at what are the three main rock types: igneous, sedimentary, and metamorphic. And then we're going to look at the rock cycle. Where are rocks created and destroyed? And we'll look at four specific pieces of the cycle: seafloor spreading, subduction, eruption, and erosion. All right, so the first rock type is igneous rocks. These are rocks that form as a liquid magma cools. And as that magma cools, crystals start to grow by piecing together elements like silica and oxygen into a crystal structure. And we can tell it's an igneous rock because it often has this characteristic texture of intergrown minerals, where the minerals are kind of fit together like a jigsaw puzzle, where they were growing next to each other as the magma cools. Now, once the magma has cooled completely, the rock has formed. It is literally now an igneous rock. And we're going to see later that we can find these magma chambers in various places on Earth. And just a quick real-life example, a common igneous rock is a granite. Vermont has a number of granites that are associated with ancient tectonics from hundreds of millions of years ago. Here's one of our most famous granite quarries, the Rock of Ages quarry in Barre, Vermont. Now the next rock type is sedimentary rock. Sedimentary rocks don't grow in a magma. They are deposited in water, usually. They can also just be deposited in air. But they're usually deposited in water, so that could be anywhere. That could be a lake, a beach, it could be a glacier or a swamp. And they are composed of literally fragments of minerals or fragments of rock. Often this will be something like sand, for example. And those fragments come to rest, usually in water, and eventually get consolidated into a sedimentary rock. So we'll see later that sedimentary rocks can often have layering. Often you can see individual grains of sand or chunks of rock in the sedimentary rock. So here's an example from Vermont. Limestone is a type of sedimentary rock. It's made up mostly of actually dead shells from dead organisms. But you can see here some of the layering in the sedimentary rock, where those layers of sediment were piled on top of each other and then eventually consolidated into rock. So the third rock type is metamorphic, and metamorphic rocks are pretty interesting. They are rocks that are formed from heating. Basically, the rock gets buried. In this example, it might be buried deep beneath a mountain range where it is hot and where there's higher pressure. And so the rock might start out as an igneous or a sedimentary rock that experiences burial, pressure, and heating. And what happens is, as it's heated and pressurized, new minerals start to recrystallize. Whatever minerals were there originally start to regrow, and we get a whole new set of minerals. Now, importantly, although we get new minerals, the composition of the rock actually stays the same as the original. And we call that original rock the protolith. The protolith is what the rock was made of before metamorphism. So it might be an igneous or a sedimentary protolith. But in any event, the bulk composition doesn't change. Whatever elements, like silica, oxygen, magnesium, were in that original rock are also in the new metamorphic rock. They're just rearranged into different minerals. The analogy for this is baking a cake, right? You put in sugar, flour, eggs, you have your composition, and then you bake it. It comes out looking totally different. It's a cake instead of a batter. But of course, the underlying ingredients are the same. The composition hasn't changed. Now, an example of this is if we start out with shale, which is a sedimentary rock, and we progressively bury it deeper and deeper under a mountain range, it actually becomes a new rock at each stage of pressure and temperature. So it might first become a slate, then with additional heat and pressure, it would become a phyllite. With additional heat and pressure, it would become a schist, and eventually a gneiss. And we'll look more at this in the future, but the main point here is that you would start with a single protolith, and depending on the pressure temperature conditions, you could end up with a very different variety of rock types. Now, a good example of metamorphic rocks in our region is the Adirondacks. These are the mountains immediately to our west. So we're here in Vermont, in Middlebury, and here's the Adirondacks of New York. And these are totally unique rocks. They're a metamorphic rocks, mostly gneisses, that were once buried 25 to 30 kilometers beneath Himalaya-sized mountains. And today we just have this little remnant of those mountains. Everything else has been eroded away off the top, and we're just left with this remnant of these metamorphic underbelly of the mountain range, and surrounded by much younger sedimentary rocks. So that's a good example of metamorphic rocks in our area. So in this next part of the video, let's look at the rock cycle. These are the processes that help to create new rock and destroy existing rock, and in the process resurface Earth and the landscape that we live on. So first I want to introduce you to a couple key ideas. One idea is called a mid-ocean spreading ridge. This is where new oceanic crust is created. Basically what happens is material from the deep mantle wells up and melts. That melted rock becomes magma and then gets injected upwards as new oceanic crust. Now, simultaneous to this, the older crust on either side of the spreading ridge is being pulled away and making room for this new crust to be emplaced and cool as oceanic crust. Okay, so this is where new material is born. Now, interestingly, we see these on the ocean floor, and we see them in the topography because all of this hot magma down here is buoyant, and it causes the whole seafloor to ride a little bit higher than the surrounding colder and denser seafloor. So if we look at the Atlantic Ocean basin, for example, here's New England, here's Africa, and we take a cross section across it, here's what it looks like. Here's New England, we go through a deep abyssal region, and then here's the spreading ridge. It's almost a 5-kilometer high mountain range beneath the ocean, where this new magma is being ejected and cooling into oceanic crust as the continents spread in opposite directions. Now, another piece or another component of the rock cycle is a subduction zone. This is where oceanic crust is destroyed. Typically, this is older, colder, and denser oceanic crust that is able to actually sink back in to Earth's mantle. And a lot of times it's going to take with it sediment that was deposited in the ocean and is sitting on top of that oceanic crust. And at subduction zones, of course, are associated with volcanoes. As that material goes down, we actually get melting of the sediment and sometimes of the ocean crust. And that creates new magma that makes its way up through the continental crust. And those magma chambers can then either cool into igneous rock or they can be erupted as lava flows. For example, like we might see in the Cascades of the northwestern U.S. We might be familiar with some of these volcanoes, Mount Hood, Adams, Mount Rainier, just outside of Seattle. So these are all active volcanoes sitting above a subduction zone. Of course, they could erupt lava, which is new rock, and they have also new rock cooling beneath them. So if we combine these two basic elements of the spreading ridge and the subduction zone, those are two key pieces of the rock cycle. We just showed how oceanic crust is created at the mid-ocean spreading ridge, and then that same oceanic crust is destroyed at subduction zones, along with whatever sediment is on top of it. But we call it a cycle because nothing is ever truly destroyed. That rock goes down the subduction zone, it gets melted, and it comes back up where it can be erupted at volcanoes, or it can cool and make new igneous rocks. Now, to complete the cycle, we need a final piece. That is erosion. The action of rivers, glaciers, soil act to break the rock down and transport it through river systems as sediment. And that sediment is ultimately deposited in the ocean, where it might make a sedimentary rock, and that sedimentary rock may ultimately be subducted back into a subduction zone, and the cycle will continue. Okay? So it's a cycle of creation and destruction. The time scale of this cycle, how long does it take? It's not a year, it's not a decade, it's not even hundreds of years. This cycle plays out over at least millions of years, and more often tens or even hundreds of millions of years. So it's a very slow cycle, but it persists over time, and it's important. It is the cycle that fundamentally shapes what our landscape looks like, what kind of rocks exist on the surface, and it's been fundamentally resurfacing Earth for billions of years. So, in summary, there were two parts of this video. We did the major rock types, and then we did the rock cycle. And so here's two questions that I think you should know the answer to by now. What are the three main rock types, and where might each one form? And then two, I'd like you to be able to sketch a cartoon of the rock cycle and label the main tectonic features that are involved. Thanks for listening, and see you in the next video.